Next up, we have Tage, who's going to tell us a bit about Argosy, verifying layered storage systems with recovery refinement.
All right. To motivate why we're talking about layered storage systems, let me start with the story. The story will tragically lack modularity, but then Argosy will come in and fix that. Story starts with Bob, a storage system developer who is writing a replication system. This replication system takes two unreliable disks, and it exports a single logical disk. The way it works is, of course, when a write comes in, it writes to both disks in turn, which ensures that your data is safe even if one of the disks fails. But this is a storage system, so Bob wants to make sure that it handles crashes at any time, for example, due to a power failure. And I'll represent a crash using this orange power symbol. The trouble with the crash is that a crash in the middle of a write operation leaves the system in an inconsistent state. The two disks are out of sync. But Bob knows how to handle this. He writes a recovery procedure, which we then run after every crash to restore the invariance of the system. And the way this recovery procedure works in this case is it resynchronizes the disks by copying from the first disk to the second. And Bob is a careful guy, so he writes a machine-checked proof of correctness that his implementation is correct. That is, the read and write operations are atomic and have the right behavior, as long as you run rep recover after every crash. And because he's using the latest verification infrastructure, his proof also handles the case of crashes during rep recover itself. Meanwhile, Alice writes a write-ahead logging implementation, which exports a transactional API and is implemented on top of the disk interface, the same one that Bob implemented. She's also careful, so she proves her code correct using a machine-checked proof of correctness. That is, the operations are atomic, as long as you log recover after every crash, because the log recovery procedure needs to clean up transactions in the log. So now you look at this picture and you think, surely we can compose these two things together, but you're also careful and you want to prove your code correct. And the trouble is that in order to implement logging on top of replication, we need to run both recovery procedures on crash. And this is a challenge for formal reasoning. Specifically, while we have a proof for both of these recovery procedures in isolation, a crash during the composed recovery procedure doesn't directly resemble a crash during either sub-recovery. So how do we reuse these proofs? And in fact, prior work cannot handle this situation. In crash horror logic, there's no way to move from a proof about one recovery procedure to a proof about another. In Yggdrasil, there's an assumption of a single global recovery procedure. And FlashX places some restrictions on recovery procedures to support composition that actually disallow both of these recovery procedures in this example. This is where Argosy comes in. Argosy supports modular recovery proofs supporting exactly the use case that we have here. So developers have proven both implementations correct separately, and Argosy provides a generic theorem that the composition is correct as well, including this composed recovery procedure. So our main contribution in this work is recovery refinement, the technique that we use to provide modular proofs. That'll be the focus of my talk here. We have two other contributions described in the paper. The first is an implementation of crash horror logic, an existing program logic, which we use to verify individual implementations correct. And second, we used Argosy and crash horror logic to verify a particular example of a layered storage system, exactly the example I presented of featuring write-ahead logging on top of replication. And finally, all of our code is backed by machine-checked proofs in the Coq proof assistant. Let's go into recovery refinement. I'll explain recovery refinement in two steps. First, I'll give some background on how to prove normal execution correctness using refinement. And then I'll talk about how to extend refinement with notions of crash and recovery execution, and we'll arrive at recovery refinement. So first, some background on refinement. With refinement, the goal is to prove an implementation correctly implements a specification interface, which will be on top, in terms of a code interface, which will be on bottom. So in the case of the replication example, replication implements a disk interface on top of two disks. How does it do that? It has a piece of code for every high-level operation, so for example, a write, in terms of the low-level operations available. And in the case of the write operation, the implementation simply writes to both disks in turn. Similarly, replication implements the read operation, and since that's all the operations of the disk interface, that's the whole replication code. And the way we're going to define correctness for replication is in terms of an arbitrary piece of code using the disk interface. An arbitrary piece of code using the disk interface will form the specification of the replication system, and then we'll specify what happens when you actually run the code, where we actually run the replication system's implementations on top of two disks. That specification is a classic idea of trace inclusion. All the specification's behaviors should be covered by should cover all of the running code behaviors. That is, after substituting the replication system's implementations. So how do we prove trace inclusion? We use an old idea of an abstraction relation. And this whole technique is also called forward simulation. Just to review, in forward simulation, the developer provides an abstraction relation R, which serves two purposes. First, it connects abstract states and code states. And second, it enforces any invariance over code states that the implementation relies on. Next, the developer proves that for any execution of the code, there exists a corresponding specification execution that preserves the abstraction relation. This diagram is all specialized to just the write operation of the replication system. But in general, the developer proves the same sort of diagram for all the operations in the implementation. So that covers normal execution. What about crashes and recovery? For that, we'll get into recovery refinement. But the first thing that we need to do is just go back to this picture of an implementation and incorporate recovery into the implementation and crashes into the specification. So note that the implementation now has a recovery procedure implemented in terms of the two-disk interface. And I want to highlight these two crash symbols. The top level crash symbol is a specification for what happens on crash that's exported to callers. This includes what sort of volatile state needs to be wiped. And the bottom layer, similarly, is an assumption about what happens at the two-disk layer on crash. And note that the top-level interface doesn't have a recovery procedure. So somehow our specification for this new implementation needs to hide recovery. We use trace inclusion as the basic idea, but we extend it to include recovery and crashes. To do so, first I'll incorporate crash semantics into the specification, and then I'll talk about how to incorporate recovery into the execution semantics. Our semantics for crash execution is intuitively atomicity. So we can crash in between any pair of atomic operations, and I'll represent that with this alternation symbol. And I'll abbreviate a crash in the middle of some larger piece of code with this jagged edge followed by a power symbol. The code uses an ASCII notation. For the recovery semantics, we know that we should run recovery after a crash in the middle of an operation. But that's not good enough. We also want to handle crashes during recovery. We want to model crashes during recovery in this specification. So right before recovery, we insert 0 or more iterations of crashes during recovery itself. So that covers the crash part of trace inclusion. And then if we just also include normal execution correctness, we arrive at our definition of correctness, which is trace inclusion for both normal execution and crashes. Now, how do we prove this? We use recovery refinement. So as the name implies, it's still going to be similar to refinement. It's still going to be a forward simulation. The first insight we have to come up with recovery refinement is that in the middle of some large piece of code, a crash in the middle of some large piece of code must occur in some operation. And prior to that operation, we can just use normal execution correctness to reason about the system. So that establishes the abstraction relation right before this operation, and we can ignore execution before that. It's already been proven by normal execution correctness. What's the specification for a crash in the middle of an operation? Well, we said we want atomicity. So either all of op2 runs, and then, and in this example, I'm just going to illustrate with op2, but you can imagine this is any operation in the system. The specification is going to be either all of op2 runs followed by a crash, or just a crash and none of op2. And that's all we need for recovery refinement. For every operation, it should be correct under normal execution in the sense of preserving an abstraction relation. And similarly, it should be correct for crashes. These two conditions for every operation in the system are sufficient to give us trace inclusion in that strong sense of any crash at the specification level covers all the executions, including crash and recovery. So recovery refinement, as I've presented it so far, only applies to a single implementation. But the story of this talk was about modularity and layering. So we want to compose these recovery refinements as well. For that, we have a theorem that composes them. And to get into this theorem, I'm first going to talk about Kleene algebra, which is the technique that we use to make these proofs more manageable, especially in calc. So in this talk, I've informally been using these symbols in the talk, but we actually have we give them a formal meaning in terms of Kleene algebra, which is a formalism that generalizes regular expressions. Formally, these expressions match transitions in a state transition system representing sequencing. This alternation symbol represents a non-deterministic choice between two possible transitions, and the star represents 0 or more iterations. So as we saw, these are exactly the tools that we need to model crashes and recovery. They not only give us the right tools to model crashes in recovery, they also give us reasoning principles, which we'll see in this proof sketch of the composition theorem. So more formally, what this composition theorem says is that if we have two stacked implementations, and each of them is a recovery refinement, then the composed implementation is also a recovery refinement, including that composed recovery procedure. So before we saw it, it's challenging to reason about this composed recovery because it doesn't, crashes during composed recovery don't directly resemble either sub-recovery. Now we have the tools to make this a little bit more formal. Before I do that, I'm just going to abbreviate both recovery procedure for what's going to happen on the following slides. I'll use rep for the replication systems recovery and log for the logging systems recovery. So now we can sort of more formalize, better formalize what it means to have crashes under recovery with the Kleene algebra notation that we've seen. For crashes during the composed recovery, we have this expression. So let me just break this down a little bit. We can either crash during the replication system's recovery itself, or that recovery might finish and then we crash during logging. When we're done crashing during recovery, finally the composed recovery runs to completion. So how do we reuse the proofs that we have above the line to prove this theorem? It seems like these two expressions don't show up. This is where Kleene algebra comes in. We can use Kleene algebra to rearrange this expression and recover those subproofs. The first thing we do is we apply a theorem from Kleene algebra called denesting to remove this alternation. Next, we apply a theorem called sliding to rearrange the parentheses around stars a little bit. And now, this new expression is much easier to reason about and is exactly equivalent. It still represents crashes during the composed recovery. So I won't give a formal proof here. You can see the code and the paper for that. But let me just give some intuition for why this is easier. So the first thing is that the replication proof establishes that after the rep recover runs, all the replication systems invariants are restored. Then in parentheses, because of the trace inclusion for recovery, we know that this code behaves like a crash during the high-level logging procedure. And now we have everything we need to apply the write-ahead logging proof, which shows that the logging recovery correctly handles crashes during recovery. And as a result, the upshot of all of this is that after running this composed recovery, including crashes during recovery, we've established the invariance of both implementations. Now, of course, this is just, I'm talking informally about restoring invariance, but we formalize this in terms of establishing a recovery refinement for the composed implementation. All of that code is implemented and verified in the clock proof assistant. Our framework consists of about 3,200 lines of code, so it's a pretty small framework. It establishes, it has a library for modeling Kleene algebra, and specifically Kleene algebra to model transition systems. We have a crash and recovery semantics, and that 3,200 lines includes proofs of the overall correctness theorem, as well as the composition theorem, all the generic meta theory. On top of that, we also verified an example with write-ahead logging on top of disk replication. And actually, two different authors wrote these two systems, and then we composed them together in a couple hours. And that example extracts to Haskell and runs using using Clock's native extraction facility. All of our code is open source, and I'd invite you to check it out. To summarize, in this talk, we've seen how Argosy provides modular proofs of layered storage systems. It appeals to Kleene algebra, both to model crash and recovery execution, as well as to provide reasoning principles that we use for our meta theory. We've seen recovery refinement, which is the condition that we need to prove a strong trace inclusion property for crash and recovery correctness. And finally, we've seen how our recovery refinement gives us modular proofs of layered storage systems. Thanks, and I'm happy to take questions.
Okay, cool. If someone has questions, come on up. Otherwise, I'll kick us off. So if after we're crashing, we're recovering an invariant, does that just mean that under normal crash roll logic, we picked the wrong invariant and we could compose if we picked the right one? Or is this somehow allowing me to distinguish between whether the thing under me crashed or not? Does that not make sense?
So one advantage of this approach is that we actually get away from reasoning about crash invariants directly. So the meta theory of Argosy never mentions a crash invariant, at least not explicitly. There's probably something implicit going on. Instead, we take an assumption about crashes during recovery and another assumption about crashes during recovery, some sort of like two proofs about two loops. and we compose those two proofs together. The way we actually prove that the write-ahead logging system and the replication system handle crashes during recovery is with crash invariance and crash order logic.
Yeah. Okay. Thanks.
Hi, Yuting Wang from Yale University, and I'm actually not sure. Are you proving forward simulation or backward simulation when you're doing the refinement?
So I call this forward simulation because it's forward in execution time.
Okay.
But we prove that the implementation behavior is a subset of the specification behavior.
Okay. So I'm just curious because in the implementation you have these iterations, iteration of a recovery process.
Yes.
There are a lot of non-determinism here.
Yes, there's a lot of non-determinism.
Yeah. So did you prove for every kind of for every step of iteration, the implementation behavior will be a subset of the specification, or?
So at the meta theory level, these proofs are just rearrangements of, they're fairly abstract.
Okay.
At a code level, like when we prove an individual implementation correct with specific code, then we have to reason about every single crash case individually.
Okay. Okay.
But that's handled by crash order logic.
Thank you.
Sweet. Thank you for a great talk.
Thank you.